Greetings everyone and welcome back to the bench. Today on the bench I have the EZ amp. If you watched my channel for a couple years, probably remember this thing. This was meant to be an easy to make, non-IC based of course, amplifier. Low cost, cut down on the components. I used Darlington transistors in the outputs. Now, for a multitude of reasons, I know designers do not like to use Darlington transistors, but they have been used in actual products, and some people like those amps. They should work good enough to make a little amplifier. And we're not talking a lot of power. I wanted this thing to be around 35 watts into 8 ohms and up to 54 ohms. So yeah, here's the old little paper on that. It's not going to have super audiophile, low distortion or anything like that. Got our little happy transistor down there. This is the JAT EZ amp project. And quick look at the schematic. If you want to freeze that, pause it. I'm not going to discuss this at the moment. But yeah, it was a lot simpler than the 501 amp. But this has a problem. When I was testing it at high frequencies, I was running it up to over 100 kilohertz. The transistors blew. Well, you have to be very careful when running that type of test on any amplifier, because, yeah, you can have problems that could blow the output. Well, so I said, well, I'll skip that and just do a power test. So I put in new transistors, and I was just running a normal power test at 1 kilohertz. And if I remember, it's been quite a while ago, over a year ago, and I think it was a 4 ohm load. And as I was running up the power, and of course I had it hooked up to the scope to see when it begins clipping, and as I was running up the amplitude, it just collapsed. Transistors blew again. What in the heck is going on here? So I tried another different type of Darlington transistor, and this time I was going to watch the scope carefully and see if I could see what's happening. Maybe there's an oscillation or something. So I run up the voltage again, and they blow out again. So are these transistors just junk or what? I mean, I bought them from DigiKey, so I know they're going to be authentic. So I was using these transistors, BDW42G and BDW47G. And by the way, I just got a notice from DigiKey a couple months ago that these are end of life. They're obsolete parts now. But these transistors I also had, and they also blew up, are the 33, the BDX33 and 34, the B version. What would cause them to blow up? I mean, it wasn't a serious power excursion or anything. The only thing I could see is maybe oscillation started, and it causes what's known as cross conduction. That's when both transistors are actually turned on significantly and heavy current flows through, which just blows them up, just kills them. because they're in the active region when that happens, safe operating area is exceeded, and it kills them pretty instantly. And of course the 501, I put it through all these tests and everything, never had a problem, never blew anything up. It went through the test with flying colors, but this amp is just, it's not an easy amp, it's a difficult amp now. So what I'm going to do is change these transistors out yet again. These are my last set. And going to run it up without a load, with a light load, maybe lower supply voltages, and see what happens. See if I can detect on the scope what is happening with this thing. Okay, the new transistors are in. I'll mount it to this heat spreader. Has the mica washers on it. This is just the heat spreader, it's not the entire heat sink. So I know some people were thinking earlier that's too small. But yeah, that's not the heat sink. Let's take a quick look at these transistors. Let me get the meter here. So we'll go from collector to emitter. Dead short. See, what is this one? This is the BDW 47. And let's check this BDW 42. .2 volts. So it's leaky. It's a very leaky transistor. This way I get 0.3. So yeah, one completely shorted and one was damaged. It's become leaky. Okay, got the power supply set in serial mode, plus and minus 5 volts. We'll start low. Current limited to 0.5 amp. Don't want to blow anything up right away. And I'm going to leave these reservoir capacitors out of the circuit right now because they can store quite a bit of energy, and if we do cross conduct it could damage the amp, and I won't be able to see what happened that quickly. So it's working again. Let's put some music through it. Okay, got the music player connected through the stereo to mono mixdown box, and yes, I've made a video on that. Let's see what happens. You can't play too much of that, but it's doing what it's supposed to do. And yeah, I don't have it on a heatsink yet because the supply voltage is low and it's not going to get very warm at all. So now what I think I'll do is hook it up and keep it at low voltage and run some tests here and see what happens. Okay, I now have the amplifier connected to the load and to the scope. Got my old Radio Shack speaker amplifier. You can This is a good example of how nonlinear your supply currents are. Listen. Very distorted. I think the song just ran out. Probably going to get copyright policed on this. Alright, enough playing around. Let's get some signals on this thing. Okay, we have a signal. Keep in mind we're running it only at plus and minus 5 volts, so nothing's gonna look that great. In fact, a little crossover notch there because the bias is so low at that low of voltage. And the clipping, see it's clipping on the bottom. It's not doing anything crazy yet. Okay, I'm gonna dare try it. We're at plus and minus 25 volts. Idle current is 40 milliamps. It goes off the screen. I gotta adjust that. Yeah, pretty normal. Let's do 4 ohms. That's doing that because the current limit on the supply, so I'll turn it up a bit. And we're still current limiting a bit. Oh, I'll just set it all the way up. There it is. It's behaving. I don't know what to think. I don't know why it blew up before, and now it's behaving. I didn't do anything different to the amp. I just popped in the replacement transistors. Okay, I'll crank it up to its normal designed operating voltage of plus and minus 28 volts. I did put this heat sink on it now. This is not adequate for normal use, but for the tests, I'm not running it for very long, so shouldn't get too hot. So go ahead and do some power output tests. I don't think I was able to get that far before, so go ahead and see what it can do. Okay, apologize about the glare. I'm doing this at daytime. I'm getting a lot of light in through the window here. We'll adjust this to clipping. Dial out the clipping. Put some waveforms on the screen. We'll take a voltage measurement. 17.77 volts RMS. 17.77 volts RMS squared divided by 8 ohm load is 39 watts. Now let's try for 4 ohms. Now we're going into oh, I gotta turn the current limit back up on the supply. It's not blowing up. This amp's behaving just like it's designed to. It's not blowing up or anything. I have no idea what happened the other 3 times. I don't know why. It just blew up during the power measurement tests. And you can see here that it's running just fine. Anyway, 16.3 something 36. I'll just let it roast there a little bit. So 16.36 squared divided by 4 is about 67 watts. And I'm just letting it run a little bit, letting it warm up. Okay, let's see what happens. Whoa, bias current is way out of line there. Could it be that it's dropping? The thing got really hot. Woo! Yeah, that's hot. That's why you want good thermal connection to your heat sink. There's the bias. As it cools off, it's falling back into line, so it's not going the wrong way. But yeah, you want the best thermal conductivity you can. Yeah, this heat sink is just not adequate for the job. It gets too hot. The bias drops right back in line. Let's see here. Let's turn the signal on. Drawing almost 2 amps. Turn that off. See how high the bias is? Because these transistors, they get really hot. The heat doesn't get out of them over to the sensing transistor that quick. There's takes time for the heat to get over there. So you can see it's dropped back already. It doesn't run away, it just gets up pretty high. Another issue is this control is at the limit of travel. See, I can only go the other way. The bias goes up, and that's as far as I can turn it down. So I'll have to make an adjustment to the design, use a different value potentiometer there, so I can turn the bias down. It's a little higher than I would run it for this amp right now. For this type of amp, I would run it probably under 50 milliamps, maybe around 40. I mean, at lower voltages, yeah, the bias is lower. See, this amp does not have a current source, a constant current source. In the voltage amplification stage, it just uses resistors here. It has a bootstrap circuit, but as far as DC concerns, this is just resistance. And as you increase the supply voltage, you're going to have more current. So it affects the bias spreader circuit here. So I have to adjust. See, I have a resistor here, and I just have to, I can keep this potentiometer, but I need to tweak it. I must have already discovered that and made some notes here. Or not. I don't know where I left off on this thing, because I pretty much buried it when it was blowing up, but it's not blowing up now. I don't know why. Okay, back on the bench. It's actually been a few days. Had some other things to take care of. But since then, I've put the amplifier onto a heatsink. I changed that 220 ohm resistor to 330. Now the proper bias setting falls about mid-travel of this trimmer instead of near one end of travel. So that's much better. I also moved the VBE multiplier transistor, or the thermal sensing transistor, onto the tab of one of the outputs, so it would respond quicker to the heat coming from the transistors. When it was over here, it takes time for the heat to come out of the transistor and be sensed by this one. So anyway, let's see what happens. And we're set for 4 ohms. There's clipping. Nothing unusual happening there. So I turn this down about here, so most of the dissipation is in the transistors, or I should say the maximum. And when I stop, I'll pay attention to the current, and it drops down pretty quick. Well, a couple seconds. So very fast response now. I saw it read 0.25, quarter of an amp. It's probably either the sampling of this when the signal changes. Yeah, it's not going to drop instantly. But still, you have the output and driver in one package on the die inside these Darlington transistors. So it's not going to be perfect. That's one reason a lot of people don't like these, is because the driver and output are in one package. So the output heats the driver up, and you get that high thermal response from that. But it's doing much better. But I think I'm going to wrap it up here. So that's the JAT EZ amplifier. Will I continue on with this? Well, I think if I was going to continue with this, I would split this into discrete components, have separate outputs and driver transistors. So get better thermal performance. But the idea was to keep this cheap, but still you can use the cheaper discrete transistors instead of the Darlingtons. Of course, I have to ask myself, does it make any sense since the JAT 501 amplifier doesn't have any of these issues? And it's a better amplifier, probably has lower distortion, though I don't know what the distortion of this is yet till I test it. And just out of curiosity, I might run some more tests on it, such as the step response and distortion tests and things like that. But that will be for the future because the video is kind of getting long. But yeah, one thing for sure with this amp and the Darlingtons, they have pretty poor safe area. I mean, at 30 volts, you only get like 1.3 amps of safe area, and it's at the second breakdown point as well. Whereas the discrete transistors like I used in the 501 will have several amps of safe operating area at that same voltage. So it might make sense to use those instead. But anyway, I'm going to wrap it up here and appreciate you watching. Appreciate the support. Catch you on the next one.